All right, in this video, we're going to take a look at what is known as the central limit theorem in statistics. So we've talked a lot about, in the past couple videos, about sampling means and standard error. So we're going to see maybe how that applies in the central limit theorem. All right, so we can create a histogram of a population, and okay, no problem. But if we take a look at sample means from within that population, how are the histograms of the sample means going to look for various populations? So let's run some simulations with Python to see what the histogram of the population is going to look like, as well as what our sampling mean histogram is going to look like. So here we have a simulation program, and I'll put a link for this in the description. Hopefully I'll remember to do that. But here, first we're going to take a look at a uniform distribution in which all the data values are roughly the same, a normal distribution, and a geometric distribution as well. So we're going to take a look at those histograms for not only the population, but for the samples as well. So, all right, let's go ahead and run this. And this is our uniform distribution. So here's our uniform distribution population, roughly about all the same height. Okay. Now, if we take samples, and I took sample sizes of 50, and got 10,000 samples, each with a sample size of 50, here is our histogram for our sample mean. So notice that our population was uniform, but our sample means, when we plot that histogram, it has a normal bell-shaped appearance to it. So our mean of our sample means and our mean of our population very, very close to each other. The square root of 50 is roughly 7-ish. So if we multiply our standard deviation by 7, we get approximately what the standard deviation of the population is. So we get that. Okay, so that's the data. If you hit, let's see, okay, yeah, or just put a hashtag symbol in front of it to comment it out. Now let's look at the data for the normal distribution. Make sure that's not indented. Okay, so our population here's our population. It comes from a normal or bell-shaped distribution as our population. Here is our sample mean. So again, we have a bell-shaped distribution. So again, notice our sample means and population means. The mean of the sample means targets the population means, and if we multiply this standard deviation by 7, we get our population standard deviation roughly. So again, our standard error using the formula and versus the standard deviation of the sample means, they're targeted values where this value here targets our standard error. So, all right. So now for a geometric distribution, let's see what that population histogram looks like and the samples from it as well. So this is a geometric one. Here's our geometric one. Again, geometric is a discrete variable, random variable. So we're typically not going to have the bars connected. Here is roughly our sample means for that. So notice we have quite a spike here, but roughly, except for a few spikes, roughly we get this bell-shaped distribution. So again, sample means, population mean, standard deviation versus standard error, and then if we take this and multiply it by 7, we get roughly pretty close to our population. So, all right, so notice that the distribution for sample means for any population is going to be normal as our sample sizes increase. So if we take larger and larger sample sizes, then that second histogram that we saw for each one is going to be normal as our sample sizes increase. And that's what's known as the central limit theorem. So as our sample sizes increase, the distribution of sample means, those second histograms we saw in each of the simulations, become normal with a mean equal to the population mean and a standard deviation equal to the standard error, the population standard deviation divided by the square root of the sample size. So that is our central limit theorem, that as we take more and more larger and larger samples from a population, and it doesn't matter what the population's distribution is, but as we take more and more samples and increase the sample size, usually around 30 or higher in each sample is pretty safe. Then the distribution of those sample means becomes normal, with a mean equal to the population mean and a standard deviation equal to the standard error. All right, so example 5, IQ scores are normally distributed with a mean of 100 and standard deviation of 16. Again, IQ scores just tell you how good you are at taking IQ tests. That's pretty much it. What is the probability that an individual has an IQ greater than 102? So for this one, we're looking for an individual IQ greater than 102 is about 0.4503. So we're not taking samples here, but we're just looking at an individual one. So if we go back to our normal distribution one, and I'll link this program in the description as well. I'll link to it, the code at least. Option 2 is observed value, and we're trying to find an area or probability, so option 1. And we're finding an area to the right, and the observed value is 102. The mean is 100. The standard deviation is 16. So we get about 0.4503, so about 45.03%. So as far as an individual is concerned, we have about a 45% chance that their IQ is greater than 102. Now, we could also have calculated probability using a z-score. This is actually a z-score for a sample, so I apologize for this. So let's just move on from there. What is the probability that in a sample of 50 people, the mean IQ is greater than 102? So now we're going to take a sample of 50 people and calculate within that sample, what is the probability that the mean is greater than 102? So the standard error, which is what we're going to use for our standard deviation of the mean, is 16 divided by the square root of 50 is about 2.263. So if we go and use our observed value here, option 2, we're trying to find the area, and we're finding the area to the right greater than 102. So the observed value is 102. Our mean is still 100, but this time our standard deviation is 2.263. So it's not 16 anymore because our standard deviation is our standard error, which is 16 divided by the square root of 50, or about 2.263. So we get about 0.1884 as our probability. So there's about an 18.84% chance that the mean IQ of a sample of 50 people is going to be greater than 102. This is where we could have used the z-score, calculating the probability there with the z-scores. But again, we have the technology and to be able to use actual values. But again, there's nothing wrong with using the z-score. Just make sure you calculate the correct z-score using this as your standard deviation. So 102 minus 100 divided by 2.263, and use that z-score. All right, part C, we have what is the probability that in a sample of 1,000 people, the mean IQ is greater than 102? So our standard error, which is going to be the standard deviation we use in our program, is now 0.5051. So now the standard deviation would be about a half. So it's gone down from where it was when we used 50 people, and it was 2.263. Okay, so we got 0.5051 as our standard error. So we can calculate our, we can use observed values again. And we're trying to find an area again, and it's going to be to the right because it's greater than. Observed value is 102, a mean of 100. This time our standard deviation is 0.5051. So we get pretty much 0 if we go 4 decimal places. What's nice about this too is, and again, I will link the description here, we could change the number of decimal places by just changing these values here to however many decimal places we want to go. So if we increase this number, we can go further out. So it's nice to have that ability to do, even though it may look scary here. You could just adjust a few things and get further decimal places. if we did go out further, we would find that the probability is very, very small. So there's about a 0.00386% chance. So about very, very small chance that the mean IQ of a sample of 1,000 people is going to be greater than 102. So as we saw with our sample sizes, we started with an individual, so a sample size of 1. And then we looked at a sample size of 50, and then we looked at a sample size of 1,000. And what we noticed is that every time we increase the sample size, we decrease the overall probability. That's because the original standard deviation is now being divided by a larger number. So like the square root of 1,000 is larger than the square root of 50, which when you divide by a larger number, it decreases the overall value. So now that by dividing by the square root of 1,000, we've just decreased what our standard deviation is. So our average spread has gone down. To put it another way, we're examining a greater variety of people. So if we have 1,000 people, we should expect to have subjects in our sample who have IQs below 102. So by opening up the sample to more individuals, we increase the chance of getting people whose IQ would be below 102, whether it's below by a significant amount or not. So again, with an individual, here's the individual probability that their IQ is greater than 102 is about 0.4503. Here is our sample size of 50. This title got shoved over to the right here in each of these pictures, so oh well. But here's our 0.1884 that we got in example 5b. And then for a sample size of 1,000, notice how it affects the X scale here for our standard deviations. So here we got 2.3 as our standard deviation. Here we got about a half as our standard deviation. We can't even see the value here because it's over on this side. We'd have to zoom in quite a bit, and we might see a little bit of shading here, but it's so negligible that we have such a small value for this third option here, where we took a sample size of 1,000. So as we increase sample size, our likelihood decreases along with it. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.